Many senior JavaScript engineers have no idea what JavaScript is even capable of. This video will transform the way that you write code and unleash your potential as a programmer. By the end of this video, you will be able to read, understand and write code like this. JavaScript is a two-paradigm programming language that supports both object-oriented programming and functional programming. And this video is your step-by-step with no steps skipped guide to functional programming so you can write more modular, testable and deterministic code. It literally goes from primitives all the way to advanced function composition. If you look up functional programming online, you might quickly get lost in academic lingo. If you're lucky, you find some kind of simple definition like this. Functional programming is the process of building software by composing functions. Functional programming is declarative rather than imperative. Side effects are isolated. An application state usually flows through pure functions. You can relax because we're going to explain all of these terms in detail, starting with primitives. Primitives are all the data types that can only hold one value at a time, and JavaScript has 7 primitives in total. You've got strings that represent text. You've got numbers that represent numerical values. Booleans represent true or false. Undefined indicates a variable has not been assigned to a value. Null represents an intentional absence of any object value. Symbol creates unique identifiers. And BigInt handles numbers larger than the standard number type can. You've also got composite data types, which can store collections or combinations of values. You've got objects, which are structures that can hold multiple values as named properties. You've got arrays that are list-like structures that hold values in specific order. Then you've got map, which is a collection of keyed data items, similar to an object but with keys of any type, and it maintains the order of insertions. Lastly, you've got sets, which are collections of unique values, like an array, but each value can only occur once. This is what an object looks like, and this is what an array looks like. A map in JavaScript is a collection of keyed data items that maintains the order of insertions and can contain keys of any data type. Create a new map. Then you can set key value pairs in the map. If you log out the map, you get an object-like representation of the map. You can also retrieve a value by key. And you can check if a key exists. You can also get the size of the map. And you can also remove a key value pair. And lastly, you can clear the whole map with just one method. A set in JavaScript is a collection of unique values that ensures that each value only appears once. Create a new set. Now add values to the set. As you can see, when you log out the set, it eliminated the duplicate apple object. You can check if a set has a value by passing the value to the has method. You can also get the size of the set that tells you how many values there are in the set. If you call the delete method, you delete a value in the set. Sets are also iterable using a for each method. And lastly, sets have a .clear method. JavaScript also has functions. You can use function declarations using the function keyword, and you can use the arrow function. A function is a process that takes in inputs, called parameters, and produces some output, usually called the return value. Parameters are variables defined in the function declaration. They act as placeholders for the values that a function will operate on. Arguments are the actual values or data passed to the function when it is called. These values replace the parameters during the function's execution. An application happens when the arguments are used to replace the function's parameters. This allows the function to perform its task using the provided arguments. A function can be a mapping, a procedure, or handle I/O operations. And a mapping is when you produce some output for some given input value. In other words, a function maps the given input value to an output. A procedure is when a function executes some steps in a sequence, and this style of programming is called procedural programming. Define a function called prepareT and push in different steps for boiling a tea into a steps array. And then you return all of the steps joined with a line break. If you log the result of this function, you just get the steps for boiling a tea, which is exactly what a procedure is. You can also have a different procedure that calculates the area of a circle for a given radius. If the radius is negative, you return an error. Otherwise, you use the usual function r² times pi to calculate the surface area. And if you log this out for a positive radius, you get the correct calculated surface area. And if you pass in your negative value, you get your error. I/O stands for input-output. Functions may handle interactions with system components such as screen, storage, logs, or network. Define an async function called fetchData that takes in a URL and then fetches the data from that URL and returns that response's JSON. And then when you call that function, you just get the data that the API returns. You've also got methods. Methods are functions that are attached to objects, and they allow you to perform operations on the object's data. In JavaScript, you can find methods on arrays, objects, and other built-in data types. Create an object for a person with a name and a greet function. This greet function is a method, and if you call that method, it locks out the person's name. Earlier in this video, you saw the use of methods on the set and the map object already, but you also have methods on primitives, because under the hood, everything in JavaScript is an object. Define a string const greeting that says hello world. Now you can call, for example, the toUpperCase method to uppercase the whole string. You can also call the replace method to replace the word hello with the word goodbye. You can also check if a string contains a certain substring by using the includes method. In this case, you can check if the word world is included in the string. You've also got a special kind of function called the no-op, which stands for no operation. That is a function that basically has no effect. It is usually used for placeholders or if you intentionally want to do nothing. In JavaScript, a no-op looks like this. Now you're going to learn about the most important building block when writing functional programming, which is pure functions. A pure function is any function defined by two properties. First, given the same input, it returns the same output, and second, it lacks any side effects. You've seen pure functions already earlier in the code examples from sum and square, and pure functions are deterministic. This is described by that first property, right? And it means that no matter where and how many times you're calling a pure function, as long as the inputs stay the same, the output will stay the same. And that makes pure functions perfect for writing reliable and testable code. Here's an example of a function that violates the first property. Create a function called generateRandomInt that takes in a start number and an end number and then returns a random integer between those two numbers. Your generateRandomInt function, even though you pass to it the same input values, start and end, you can get different output values. That is because it uses mass.random in its implementation. Here's a function that violates the second property of pure functions. Define an external array outside of a function called side-effecting function. And then inside of that implementation, whenever you call it, you push a new value into that array. When you now call the function as a side effect, it modifies that external array. Even though the side-effecting function returns something, because it pushes something to an array as a side effect, you can meaningfully use it without using its return value. Eric Elliott says, a dead giveaway that a function is impure is if it makes sense to call it without using its return value. For pure functions, that is a no-op. Another important concept you need to know about is idempotence. Idempotence means that no matter how many times you repeat an operation, after the first application, the result stays the same. For example, setting a value to 5 is idempotent because no matter how many times you set that value to 5 again, the value remains 5. All pure functions are idempotent, but not all idempotent functions are also pure. Idempotent functions can have idempotent side effects. A pure function cannot. For example, you can have a function that deletes a record from a database, which is a side effect, and deleting the record again, subsequent calls, do not change the database, right? So all additional calls do nothing. Create a new set, and then create a function that adds items to that set. If you call the addItem function twice with the same value, only the first time the value gets added to the set. That is because adding items to a set is idempotent. The second call obviously works. Idempotent functions without side effects have a feature known as referential transparency. That means when you have a function call like this, where you square the number 7 with a pure function and capture the result in a variable, you could change your function call with the result without affecting the meaning of your program. In this case, you can just hardcode the value to 49 and your program would still work the same. A language needs 3 features to support functional programming. First, first-class functions. Second, closures. And third, a concise lambda syntax. First-class functions means that you can assign functions to variables and JavaScript treats functions as first-class citizens. This gives you 3 things. First of all, you can pass functions as arguments to other functions, you can return functions from functions, and you can assign functions as values to an object's keys. Here's how you can store a function to a variable by defining a function greet that is the result of a function expression. You can define a second function, shout, that takes in a function as an argument, and you can then pass the greet function to the shout function, which executes it. You can also define a function multiply that takes in the multiplicand and then returns another function that takes in the multiplier and then returns the result of the multiplication. That allows you to define a function double by just passing 2 to the multiply function, and then you can call it with 5 to get the output 10. If you are a React programmer and you want to learn what first-class functions enable in React, check out this video that teaches you about higher-order components in React. The link is in the description below. First-class functions also enable something called a higher-order function. And you saw them already in the previous example of the multiply function, because when multiply takes in a number, it returns to you a function. And any function that takes in a function and returns a function is called a higher-order function. Create a function greet and a function identity. And when you now pass greet to the identity function, because the identity function returns a function, it is used as a higher order function. The multiply function hit another key concept, which is closure. Closure is when a function is bundled together with its lexical scope. In other words, when you have a function with an inner function, then the inner function still has access to variables defined in the outer function scope. And a closure always is created at function creation time whenever any function is created. To use a closure, define a function inside another function and expose it by returning the inner function or passing it to another function. The inner function can access variables in the outer function scope even after the outer function has returned. Closures serve 3 purposes. They enable data privacy. In functional programming, they give you partial applications and currying, and they act as parameters for callbacks and higher order functions such as map, filter, and reduce. You're going to see examples for the second and third purpose soon, but let's take a look at the first purpose, which is data privacy. Create a function called createCounter, and inside of the scope of the createCounter function, create a count variable. This counter variable is captured in the closure of the createCounter function. Then create a function increment that increments the count by 1 and then returns the count. Now you can call the createCounter function to create one counter and call it again to create a second counter, and then you can increment the first counter by just calling it. If you then increment the second counter, it starts again from 0. That is because both of these functions capture their state in their respective closure. Now when you call the counter function again to capture a count, you can increment that count and mutate that count value, but as you can see, when you call the counter function again, the inner state of the function stays unaffected. No outside influence can influence the state of the count variable captured in those closures. In order to increment it, you need to call the respective counter. This matters because some applications require data privacy, and a common pattern is usually to prefix any private variable with underscore underscore. However, junior developers might not know that underscore underscore means do not mutate this key, so they change it. And then senior developers sometimes think they know better, so they also ignore it and just change it. Closures is the only way to reliably enforce data privacy for everyone. In the beginning of this video, you learned that functional programming is declarative. But what does that mean? Imperative code describes how to do things. The code contains the specific steps needed to achieve your desired result. Declarative code, on the other hand, describes what to do. The how gets abstracted away. In other words, imperative programming is about defining the process to reach an outcome. This is known as flow control, where you describe each step of the process. Declarative program, on the other hand, is about defining the outcome, known as data flow. Here you describe what you want to achieve, and the system figures out the steps to get you there. Here's an example for imperative code. Define an array of numbers and an empty array. Now use a for loop where you push each doubled number into the array. Because you're describing each step, this is imperative programming. And here is another example for imperative code, but this time with a custom function. Create a function filter evens that takes in an array of numbers. Now define an index variable and initialize it with 0. Using a while loop, you can iterate through the numbers, and whenever a value is odd, you remove that value from the array. And if the value is even, you just increment the index. Now define an array of numbers and pass it to your filter evens function, and it will mutate the array to only contain the even numbers. Before you see an example for declarative code, you need to understand immutability. Immutability in programming means that a value or object cannot be changed after it has been created. And any change to the value or the object results in a new value or object. Create an original array. And now if you want to add a number to that array in an immutable way, you just spread the original array and then pass in the new number to the new array. And if you now log out the original array and the new array, then you will see that they are different from each other. Similarly, mutable state is any state that you can change after you created it. Create an array, and even though you define it with const, when you call push on it, it modifies the original array, as you can see when you log it out. Immutability is a central concept in functional programming because with it, your data flow is preserved, your state history is maintained, and it prevents strange bugs from creeping into your software. Non-determinism equals parallel processing plus mutable state. Martin Odersky. You want to have determinism so that your programs are easy to reason about, and you want to have parallel processing so that your apps stay performant. Generally speaking, functional programming makes your app more modular, more easily refactorable, more testable, and more deterministic. Another key concept that you need to understand is the concept of abstraction. Abstraction is when you take the complex realities and hide them and only expose the necessary parts of your objects or your system. There are two types of abstractions: generalizations and specializations. Generalization is when you create a more universal form of something for use in multiple contexts. This process identifies common features among different components and develops a single model to represent all variations. Generalization is what most people have in mind when they think about abstraction, and what Eric Elliott refers to when he says junior developers think they have to write a lot of code to produce a lot of value. Senior developers understand the value of the code that nobody needed to write. Specialization, on the other hand, is when you apply the abstraction to a specific use case and add what makes the current situation different. The difficult thing about abstraction is that there's no good rule of thumb that tells you when you need to generalize and when you need to specialize. You just need to learn and develop a feeling for it with your experience. But what you're going to find is that abstraction is the key to simplicity. Simplicity is about subtracting the obvious and adding the meaningful. John Maeder. Using functional programming, you can create the most beautiful abstractions. And I know that at this point, you are probably starving to see some examples of functional programming, but you gotta hold out a little bit longer because now you're gonna see the examples for declarative programming, which will also show you abstraction and immutability. Remember, declarative programming is about what to do. And the perfect example for declarative code are the native array methods like reduce, filter, and map. And you're going to see examples for all three, but you're going to start with the map method. The map method essentially does the same as the for loop example that you wrote earlier. The code is just more concise. Create an array, const numbers, and then call the .map method on that array and pass to it a function that doubles each number. The output will be each number in that array doubled. Map is the perfect example for an abstraction because map is removing the obvious, which is iterating over the array. The only thing that you supply is the meaningful, which is the function that you pass to the array that tells map what to do with each element in the array. So since the map method takes in a function, it's a higher order function. And the thing that you supply is supplied using the concise lambda syntax that we talked about earlier, which in JavaScript is just the arrow function. And map is immutable. You can verify this by mapping over any array using the identity function and then comparing your results to see that they are not the same, even though they have the same content. Create an array of numbers with the numbers 1 through 5 and then map over that array using the identity function to create a clone. If you compare the original array with the clone using the strict equality comparison, you see that they're not the same. You might be asking yourself, isn't that wasteful and generating tons of unused data? Well, kind of, but compared to what modern computers are capable of, the data amount is actually tiny. And also, JavaScript has garbage collection, which clears up your unused memory. Now, let's take a look at the next array method, which is the filter method. Create an array of fruits with the content apple, banana, and citrus, and then filter through your fruits to only include the fruits with the letter A. And what you're going to get back is a new array containing only the apple and the banana. The filter method takes in a special function called the predicate function. A predicate function returns a boolean that's either true or false and determines whether a given element should be included in the resulting array. And obviously filter is also immutable. The last array method that you want to know about is the reduce method. And reduce processes an array into a single value. So the reducer function takes up to 4 arguments, which are the accumulator, the current value, the index, and the initial array, but it is most commonly used with only the accumulator and the current value. So take a look at this example that shows you how to sum an array of numbers. In this example, reduce is called on the numbers array. The sum reducer function is used to add each number to a running total, starting from 0. Here's what happens at each step. Step 1. The accumulator starts at 0, the initial value. The current value is the first element of the array, which is 1. They are added together to make the new accumulator value 1. The accumulator is now 1. The current value is the next element in the array, which is 2. And adding these gives 3. Now the accumulator is 3 and the current value is 3. Adding these gives 6. And lastly, the accumulator is now 6 and the current value is the last element, 4. Adding these gives the final result of 10. The reduce method is the most powerful array method because using it you can implement map and filter, but you cannot use map to implement reduce or filter, and you cannot use filter to implement map or reduce. To implement map using reduce, you can create a reducer function that takes in an array and the map function, and then reduce over that array and just concatenate a new array using the spread method and use the map function on each of the current values. And then you can take an array of numbers and map over it using your custom map method. For the filter using reduce, the reducer function takes an array and the filter function, and then, similar to what a predicate does, depending on whether the filter function is true or not, you either add the current value to the accumulator or you just return the accumulator alone. And now again you can take an array of numbers and filter through it using your custom filter method. Now you need to learn the difference between expressions and statements. A statement is frequently used in imperative programming, and it is a piece of code that performs an action. The first example for statements are loops, for example the for loop and the while loop. You also have control flows, such as the if-else statement and the switch statement that can define different cases. And lastly, you've got error handling, such as the try-catch statement and the throw keyword, which is used to handle errors and to throw errors. Except for functions, when you see curly braces in your code, you're likely dealing with a statement. And now you also got expressions, and declarative code favors expressions. Expressions is code that evaluates to a value. For example, you've got literal expressions, such as the number and a string. You've got arithmetic expressions, such as the plus operator or multiplying two numbers. You've got logical expressions, such as the operand selector operators. You've got function expressions, for example, an anonymous function keyword or the arrow function. There are also object and array initializers to create new objects and arrays. You've got property access expressions to access elements in objects or arrays. And lastly, function calls are also expressions because they immediately evaluate. You are about to unlock a new superpower, so lock in. Eric Elliott says that all software development is composition, the act of breaking down a complex problem into smaller parts and then composing those small solutions together to form your application. And whenever you're using functions together, you're composing them. Define a function increment that takes a number and increments it by 1, and a function double that takes a number and doubles it. Now you can define a function doubling that takes in a number and first doubles it, and then it takes the doubled result and passes it to the increment function, and it finally returns the incremented result. This is imperative function composition, and when you call the double inc function with 5, you get back 11. As with anything in life, when you do it consciously, you do it better. And the code that you just saw is actually not the ideal way to write it, because the more code you write, the higher the surface area for bugs to hide in. The obvious exceptions are docstrings, for example, or just giving your functions verbose names so your readers can understand your code easily. And the best way to reduce the surface area for bugs is to avoid the capturing of intermediary results. Write the same code again, but this time write the double inc function as an arrow function that makes use of implicit returns, and pass the result of the double function directly into the increment function. In mathematics, function composition is taking two functions, f and g, and applying one function to the result of another function. H of x equals to f composed with g of x equals to f of g of x. The hollow dot is called the composition operator. In mathematical notation, if you have two functions f and g, and their composition is written as f composed with g, this means you first apply g to x, and then apply f to the result of g of x. For your example, f of n is equal to n plus 1 and g of n is equal to 2n. The composition h of n equals to f of g of n calculates 2n plus 1. Generally, mathematicians use the letters x, y and z to denote any variable, but in this case you're using n because that subtly hints at the fact that your variable is a number, but the different name has no impact on the result. You can abstract away the composition operator into a function called compose2 that takes two functions and composes them in mathematical order. Create a function called compose2 that takes in two functions named f and g, and then the initial parameter x, and then it composes f of g of x. And then you define increment and double again, but now you compose them using your new compose2 function. And the result is still the same. Compose2 can only compose two functions at a time, but get ready, because this is where things get powerful. If you want to compose an arbitrary amount of functions, you can write a generalized compose like this. Compose takes multiple functions as its arguments and collects them into an array fns via the REST syntax. It then returns a child function that takes in the initial value x and returns the array fns with the reduce-write method applied to it. By the way, reduce-write works exactly like reduce, just that the elements in the array are processed in the opposite order. The reduce-write method then takes in a callback function and the initial value x. That callback function is the heart of compose. It takes in the accumulator y, starting from x, and the current value f, which is a function from the array fns. It then returns that function f, called with the accumulator y. The result of that function call then becomes the accumulator y for the next iteration. Here the next function f from fns gets called with that new accumulator value. This repeats until the initial value x has been passed and transformed through all the functions from the array fns. So now let's walk through all of the steps when you apply the compose function to your three functions. The initial value is 3, and you pass this initial value 3 to the first function, which is the increment function, so 3 plus 1 is 4. Then you pass 4 into the second function, which is the double function, and 4 times 2 is 8. And now you pass 8 into the last function, the square functions, and 8 squared is 64. The compose function here is written using the mathematical names. If you want to write it using the usual names that you are used to from any reduce function, you would write it like this. In this version of compose, you can name the functions array as functions so it's clear what they are. Then you take in the initial value, and instead of calling it x, you call it initial value. And then you reduce right over the functions, and then inside of the reducer function, the accumulator is either the initial value or the last result of the previous function call. And then you just call the current function on the current accumulator. Now you can compose the three functions just like you did before. You might find it unintuitive to compose functions in mathematical order. Luckily for you, there's also the pipe function that allows you to compose functions in reverse mathematical order, so from left to right. Pipe is defined exactly like compose, just that instead of reducing right, you just reduce over the functions. And now, when you compose your functions with pipe, notice how increment and square are flipped, and increment is the first function and square the last, so that your function still behaves the same. You might be asking yourself right now, Jan, what if I have to debug code, right? Then I have to capture variables, right? So I can log them out. You actually don't, because there's a helper function called trace that is a higher order function that you can use to debug your compositions. To define trace, you create a higher order function that first takes in a message and then the variable that you want to log out, and then as a side effect, you log out the message and the variable and you simply return it again. And here is how you can use it. So first you define a pipe function again, and now you define the trace function. And now when you have your increment, your double and your square function, you can just inject the trace in between the function calls, and when you now call the composed function, as a side effect, it will now log out the intermediary results. In the functions that you just saw, trace, pipe and compose, you saw a new technique being used called currying. And currying is when a function takes in its arguments one after another instead of taking them all at once. Define a function called addUncurried that takes in both numbers at the same time, and then define a function called addCurried that first takes in the first number and then returns a function that takes in the second number before returning the final expression. And when you call both functions, you have to pass in both arguments simultaneously to addUncurried, while addCurried takes in the arguments one after another. With arrow functions, these definitions can become one-liners by leveraging their implicit returns. You can visualize it like this. addCurried is a function that takes in a and then returns a function that takes in b, and this function now returns the result of the sum a plus b. You can curry any function. For example, you can create custom map and reduce functions. Map takes in 2 parameters and reduce takes in 3. The number of parameters a function takes in is called arity, and they are shorthand terms for 1, 2, and 3 arity functions. You've got unary, which is when a function takes in 1 parameter, for example, the square function. You've got binary, which is when a function takes in 2 parameters, which is your custom map function. And then you've got ternary, which is when a function takes in 3 parameters, which is your custom reduce function. And it's important that you understand arity in the context of currying, because when a function is curried and you call it, then you reduce its arity by 1 until it returns its final result. And when you compose functions, the initial function can have any arity, but every following function in the composition has to be unary. Here's what it looks like when you compose a ternary function with a unary function. Define a function add3 that takes in 3 numbers, and then a function double, and now you can compose them with pipe, and as you can see, the resulting composition takes in 3 parameters. If you want to practice what you just learned, you can pause this video and do a little exercise, which is to create a custom filter function that takes in the predicate and then an array, and then filters that array based on the predicate. Wouldn't it be nice to have a custom curry function that can curry any function? Well, there is. This example contains mathematical names for the variable names. If you want to have more descriptive variable names, then you can write curry like this. Curry uses recursion, which is when a function calls itself for the purpose of iteration. Let's break it down. You've got f, or the target function, which is the original function you want to curry. Then you've got array, or the collected arguments, which is an array to collect the arguments of all currying calls. Each cycle, except for the last, new arguments get added. Then you've got args, or the current arguments, which is an array of the arguments taken in with the current invocation of the curried function, in this case, addCurried. Then you've got a, or all arguments, which is an array of arguments concatenated from the current arguments and the collected arguments from the previous calls. When you call addCurried with 1 or more arguments, these current arguments get taken in as args in the child function of curry. This child function returns another function, which you could call the grandchild function of curry. The grandchild function immediately invokes itself with an array concatenated from the collected arguments array and the current argument args, receiving these values from its grandparent and parent closure. It takes this new array as the all arguments a and checks if the all arguments a contains the same or higher amount of arguments as the target function f is declared with. If yes, this means all necessary currying calls have been performed. It returns a final call of the target function f invoked with all the arguments a. If not, it recursively invokes curry once again with the target function f and the new all arguments a, which then get taken in as the new collected arguments array. This repeats until the a.length condition is met. As you've learned earlier, an application is when a function replaces its parameters with the arguments so that it can then perform its task using the provided arguments. If you define a function add that takes 2 numbers and adds them, you can define a function inc that uses this add in its definition by supplying 1 as one of the arguments. A partial application is when you call a function with some but not all of its arguments, and what you get back is a new function that has some of these arguments captured in the closure, and you can capture that function in a variable. And this new function will take in less parameters than the original function because it only takes in the remaining parameters. And partial applications are useful for specialization when you want to save a function with some common values captured in the function's closure. Create a curried add and then capture 1 as the first argument to define a new function called inc. Because you never mentioned the parameters of inc, this is called point-free style. You can also define inc in a pointed style by explicitly mentioning n. Inc is defined in what you call point-free style, which is when you define a function without explicitly mentioning its arguments. And this is done by capturing 1 in the closure of the add function. For you to compose functions, your functions need to meet 2 requirements. First, the data last principle, and second, the data needs to line up. Data last means that your function needs to take in the data that it operates on as the last parameter. The 2 functions that you saw earlier, the add function and your multiply function, for them this principle does not matter because they are commutative, which means that they can take in the arguments in any order. You're gonna learn the importance of the data last principle using division, because division is not commutative, so you can use a custom divide function to illustrate the problem. So imagine you have two functions, divide data first and divide data last. And now you want to define a custom half function that takes in a number and divides it by 2. Using the divide data first function, you can define it in point-free style, but using the divide data last function, you cannot, because the division is not commutative and the order of arguments matters. If you try to use the divide data first function to create half in a point-free style, that fails, because the function that you get is nonsense. But using the divide data first function, you can only create the half function by mentioning the argument explicitly, which makes it pointed. The bottom line is that in order for you to be able to use partial applications, you need to write your functions using the data last principle. One of the best libraries that uses the data last principle is Ramda. And here's an outlook at what you can do when you're using the Ramda library. Size is the function that can take an object or arrays and returns how many properties or elements it has. Remember, functional programming is meant to improve your code by making it more bug-free, modular, testable, refactorable, understandable, and deterministic. So if you mix imperative and declarative code, like here in the definition for rename keys, that is totally fine. Relax if you need some time to understand implementations like this. Just go with what is easiest to write for you. You don't need to force functional programming at all. You can call rename keys with key replacements and an input to return a new object with its keys renamed according to the key replacements. Now the second principle is that your data needs to line up, and only with the data last principle can you compose functions, because only with the data last principle can you get your functions in a state where the input types and the return types of your functions line up so that you can compose them. In other words, if you have a function that takes in a string and returns an object, you cannot compose that with a function that takes in an array and returns a number. Here's how that looks like in code. Create a function echo that takes in a value and the amount of times, how many times that value should go into an array, and then create a function called double map that takes in an array and then doubles each number in that array. Now you can compose these functions to a function called echo and double map. And when you call echo and double map, then you get an array back that doubles each number that you gave to the function. Remember, echo and double can be binary even though it ends unary. But when you try to compose echo and double map in the wrong order and you try to call it, then it throws an error, because the double map function defined in the wrong way expects an array instead of two numbers. Now it's time to tie everything together that you just learned. And we're gonna do that in the form of an exercise. And if you wanna code along, you can do that. Otherwise, sit back, relax, and enjoy the show. And the exercise is to create a function called Mozart that takes in an array of numbers. And then it filters that array of numbers so that it only contains the even numbers and rejects all the odd numbers. Then you double all of the leftover numbers, and finally you sum them all up and return the result. Remember to break down your functions to their most basic abstractions and use point-free style. Pause the video now and do the exercise if you want to. Otherwise, here's the solution. Start by creating the custom curry magic spell that you learned earlier. Then define a custom add function using your custom curry function and create a curried multiply function. You can then use a partial application to create your inc function and another partial application to create your double function. And then you define an isEven function that takes in a number and returns true if the number is even. Then you create a custom map function, a custom filter function, and a curried reduce function, and use them to create a double map function by partially applying the double function to the map function, a custom filter even function by partially applying the isEven function to your filter function, and then you can create a custom sum function by partially applying the add function and 0 as the initial value to your reduce function. Now it's trivial to compose your Mozart function by just composing filter evens, double map, and sum using the pipe. If you then pass in an array that contains the numbers 1 through 5 to the Mozart function, it correctly returns 12. So you might be asking yourself right now whether this isn't more complicated than just piping the functions like this, where you define the Mozart function by taking in an array of numbers and then just piping the filter function, piping the map function, and piping the reduce function while defining all of their respective functions in line. The code with the chaining and the array methods is obviously easier to read than the code where we used all of the techniques that you learned throughout this video. But you want to use these techniques in the right settings. Remember, Yagni, which means you ain't gonna need it, and KISS, which means keep it simple, stupid. As your app grows in complexity and scales, you will need to use these techniques if you want to write the cleanest code possible. And functional programming allows you to write the most maintainable, testable, deterministic, and modular code. Now you know the 20% of functional programming that gives you 80% of the results. And if you want to see how to apply these techniques in a real-world setting, watch this video that shows you advanced functional programming techniques. I love you very much. Thank you so much for watching, and subscribe if you learned something.